Hello and welcome. Today we're looking at AQA GCSE Physics for Unit 1 for Energy. If you find these videos useful, you can get access to all Paper 2 whole unit videos for biology and chemistry by becoming a channel member. Details in the description below. For now, let's get going. We're going to start off by looking at energy stores and changes in systems. Energy stores and systems. A system is an object or group of objects. This will get you the mark if you are asked what a system is in a physics exam paper. Energy stores. Thermal energy. This is energy due to the temperature of an object, for example, a hot cup of tea. There are three potential energy stores that we should know about. They are gravitational potential energy, and this is the energy gained by raising an object above the ground. An example being a skydiver. Elastic potential energy. This is energy in stretched or compressed elastic objects. A common example is a spring, but it could also be an elastic band or even a rubber ball. Chemical potential energy. This is energy in chemical bonds, usually in batteries, in food, and in fuel. So these are the potential energy stores. Kinetic energy. This is another energy store, and it's the energy of a moving object due to its motion, a common example being a car. Then we have magnetic. This is attracting or repelling by the poles of a magnet. So there's two magnets with opposite poles near each other, and we get the attraction of those two magnets. We have electrostatic. This is attracting or repelling by positive and negative charges. For example, two charged objects like this, oppositely charged, plus and minus, we get attraction. And finally, we have nuclear. This is energy in the nuclei of atoms. We'll look at this in more detail in a later unit. We also have energy transfers, ways in which energy can be transferred, and these are heat, from hot to cold, for example with that iron. We have sound, we have electrical, we have radiation, including light, and we have energy transfers by a force, and we would refer to that as mechanical. So those are the ways that energy is transferred from one place to another. Let's take a closer look at kinetic energy. This is the equation. You'll be given all the equations in your GCSE physics exam. Kinetic energy is 0.5 times mass times speed squared. The units for energy are joules, for mass kg or kilograms, and for speed m/s or meters per second. The symbols are as shown on the screen there. And we can look at an example. Imagine we have a car with a speed of 15 meters per second and a mass of 520 kg. You could pause there and give this one a go quickly if you like, but if not, kinetic energy is 0.5 times 520 times 15 squared. And if you put that into your calculator, you get an answer of 58,500 joules. Occasionally, they might ask you to do a conversion. This in kilojoules is 58.5. found by dividing by 1,000. Something useful to know that has been assessed on past papers: if you double the mass when we're looking at kinetic energy, the kinetic energy will be times 2 or doubled as well. If we double the speed, however, the kinetic energy will be times 4. And if we double the mass and the speed, we will have kinetic energy times 8. As I said, this has been assessed before, so it might be worth knowing for your exam. Let's take a look at gravitational potential energy. GPE, or gravitational potential energy, is mass times gravitational field strength times height. Mass is measured in kg, gravitational field strength is in newtons per kilogram, and height is in meters. Gravitational potential energy, being an energy, is going to be measured in joules. These are the symbols for that equation, and they will also be on your equation sheet. G will be given, so gravitational field strength will be given in the question. It's usually 9.8, but that will be given to you in your exam paper if you need to use it. Let's have a look at a couple of examples. Calculate the gravitational potential energy of the swimmer. G is 9.8 newtons per kg. The swimmer has a mass of 50 kg and a height above the water of 3 meters. You can give this one a go if you like, but here is the answer. GPE is 50 times 9.8 times 3. If you put that into your calculator, you'll get an answer of 1,470 joules. Here's another example. This time we have to calculate the mass of the swimmer. The GPE is given as 1600 joules, and G again is given as 9.8 newtons per kilogram. The height of the swimmer above the water is 3.5 meters this time, and we would do this by substituting in the values into the equation. 1600 equals mass times 9.8 times 3.5. Rearranging the equation will give us 1600 over 9.8 times 3.5. Important to put that in brackets. That will give us the mass, and if we put that into our calculator correctly, we'll get a mass of 46.6 kilograms for that one. So that's gravitational potential energy and a couple of examples. Next, we take a look at elastic potential energy. Energy is transferred to a spring as elastic potential energy when it is stretched or when it is compressed. The spring constant tells you how stiff a spring is, and it can be measured. Here is the equation that we need to be able to use, but again is on the equation sheet. Elastic potential energy is 0.5 times spring constant times extension squared. Don't forget the squared. Many students forget to square and then get a wrong answer. The spring constant is measured in newtons per meter, extension in meters, and elastic potential energy, being energy, is measured in joules. Here's the symbol equation, and here is a simple question. The extension of a spring is 0.08 meters. The spring constant is 160 newtons per meter. What's the elastic potential energy? We substitute into the equation, very straightforward. Don't forget to square the extension. And we end up with an answer of 0.512 joules. Next, we have a slightly trickier question. A spring has an elastic potential energy store of 4 joules when stretched by 8 centimeters. Calculate the spring constant. The first thing, and very common thing we have to do in all of your science exams, is to do a conversion. So 8 centimeters into meters will be dividing by 100 to get 0.08. So if we substitute into the equation, we have 4 equals 0.5 times k, the spring constant, times 0.08 squared. If we square out, this is what we have, slightly simpler. And we can have 4 divided by, open bracket, 0.5 times 0.0064, close bracket. The brackets are quite important there. Will give us k. An extra step, but you don't need to do this step, is to simplify like this. And then we get a value of k, the spring constant, as 1250. Don't forget the correct units, which are newtons per meter. So that's elastic potential energy and 2 examples. Next, we're going to take a look at changes in energy stores, and we're going to look at 3 examples. The first example is a ball being thrown upwards. Remember, at all points in the rise of the ball, gravitational potential energy plus kinetic energy is constant. That's if we ignore any friction with air. Let's look at this a bit more visually. We have a ball here. Let's say that its gravitational potential energy at the start is 0, and it's thrown up with a kinetic energy of 20 joules. About halfway up, the gravitational potential energy increases because its height increases, and the kinetic energy decreases. However, adding the GPE and the KE makes 20 joules, just as it did when it was at the bottom of its rise. When we get right to the very top, the GPE is now 20 joules, and kinetic energy as it gets to the top has become 0. However, if we add 20 to 0, we get the same value as we did throughout the journey of the ball as it is thrown upwards. So let's put that back so it's there for your notes. And here is a question that you might find on the higher paper. A ball is thrown upwards with a speed of 5 meters per second. It has a mass of 0.26 kg. Calculate the maximum height of the ball. G is 9.81. Luckily for this question, there are no conversions to do, but always look out for conversions. And we can start off by looking at the kinetic energy when the ball is thrown. That would be half times mass times speed squared. And therefore, if we substitute in the values, half times 0.26 times 5 squared, and those values come from the question, gives us 3.25 joules. All the kinetic energy is transferred to GPE, or gravitational potential energy. Remember, we are ignoring friction with air for this question. That means GPE at the top of the rise is equal to kinetic energy at the start. So GPE is mass times g times height. That will give us 3.25 is equal to 0.26 times 9.81, given in the question, times height. We can rearrange 3.25 divided by 0.26 times 9.81 in brackets. That will give us the height, which is 1.27 meters. So that's the kind of thing you might be asked on a higher paper or for a higher mark question, because two equations are required. Example number 2, a car braking steadily. Here's our car. It brakes steadily from a journey that it was on, and at all points the thermal energy of the brakes plus the kinetic energy of the car is constant. So again, let's say the kinetic energy is 100 joules. That's a little bit small, that number, but it's just here for an example. So the kinetic energy is 100 joules. The thermal energy of the brakes before they are being used, let's say, is 0 joules. As the car slows down, the kinetic energy becomes less, let's say 50 joules. Therefore, the thermal energy will be 50 joules as well. And finally, as the car comes to a halt, kinetic energy becomes 0, and the thermal energy of the brakes is 100 joules. All the kinetic energy has been transferred to the thermal energy in the brakes. Let's put those back in for our notes. And the final example is a collision. The kinetic energy of a car is transferred to heat and sound, which dissipates or spreads into the surroundings. So here's our car, here's a wall. The kinetic energy of the car, as a simple example, is 100 joules. It travels, hits the wall, we have a collision, and that energy of kinetic energy is transferred to sound and heat, and that will add up to be 100 joules. All the kinetic energy has transferred to sound and heat, which then spreads or dissipates into the surroundings. And remember, kinetic energy here therefore is 0 joules. Next, let's take a look at energy changes in systems. The amount of energy stored in or released from a system as its temperature changes can be calculated. Again, here's another equation that you'll be given in your exam. Change in thermal energy, in heat energy, is mass times specific heat capacity times temperature change. Mass is measured in kg, specific heat capacity in joules per kilogram degrees Celsius, and temperature change will be in degrees Celsius. Change in thermal energy, being energy, will be measured in joules. And the symbols for that equation, also given to you in the exam, are shown there. Next, we're going to take a look at the definition of specific heat capacity. Specific heat capacity. This is the amount of energy required to raise the temperature of 1 kilogram of a substance by 1 degree Celsius. If you are asked the definition of specific heat capacity in the exam, that's what will get you the marks. Let's take a look to see what it means. Here I have two different materials. One is copper metal and the other is aluminium metal. They are both 1 kilogram, and what we're going to do is transfer 1000 joules of energy to each one. You would expect that the temperature might raise by the same amount, but in fact, the temperature for the copper goes up by 2.6 degrees C and the temperature for aluminium only by 1.1 degrees C. You don't have to memorize those numbers. This is just the idea that you could put the same amount of energy into two different materials of the same mass and get a different temperature rise. You can see that in a bit more detail in a graph like this. As the energy transferred increases, the temperature increases, and that's for the copper, and that one's for the aluminium. For the same heat energy supplied, we get a different rise in temperature. So if we picked one value of energy transferred, we could see that it's at that position there for temperature for aluminium, and it's higher for the copper, for the same energy transferred. Let's look at required practical number 1. The investigation to determine the specific heat capacity of one or more materials. Here is a 2D diagram of a 1 kilogram mass of metal. We would measure the mass of the metal block in kg using a balance. We would add insulation to the block, so there's our insulation. Then we would insert an electrical heater into the large hole in the block, right there. We would then connect the power pack, ammeter and heater in series and the voltmeter in parallel, this is how that should look. We have the ammeter in series, in other words, in the path of the electric current, and we have the voltmeter across the heater, as shown in the diagram. You must get those the right way around to get the mark in the exam. We then add a small volume of water into the other hole and place the thermometer in the hole. The water is there to help transfer the heat from the block to the thermometer. Next, we will set the power pack to 10 volts and switch it on and measure the potential difference or voltage. Please remember, when you're answering questions, you can either use potential difference or voltage in your answer. In exam questions, they will always use potential difference. We would then measure the temperature and start the stopwatch. We would record the temperature every minute for 10 minutes. Here is a graph that we would end up with, something like this. Energy transferred on the x-axis and temperature in degrees C on the y-axis. Here are a set of values, and if we join them up with the line of best fit, we notice that it doesn't rise equally in all parts. This part here at the beginning is there because it takes time for the heater to warm up and for the heat to spread through the metal. That's why we get that little lag at the beginning. Next, we would use the equation to calculate the specific heat capacity. The equation was given at the beginning of this slide. The mass of the block, let's say, is 1 kg, and the temperature rise went from 22 to 38 degrees C, so the temperature change for our equation is 16 degrees C. We could rearrange the equation. Specific heat capacity is energy transferred divided by mass times change in temperature. However, we're not given the energy transferred directly in this scenario. So this is where we need to use the ammeter and the voltmeter. Power is voltage times current. This will be given to us on the equation sheet. And energy transferred is power times time. This will also be given to us. Let's say the voltage was 10.2. Let's say the current was 2.7 amps. And the time was 10 minutes. That's 600 seconds. We need the time in seconds, and the 10 minutes was given to us in the question. So then energy transferred is voltage times current, which is 10.2 times 2.7, times time, which was 600 seconds. And that gives us energy transferred of 16,524 joules. Sometimes the experiment is simplified and done with a joule meter, which gives you the energy transferred directly, and you don't have to calculate it. But if you do, that's how you do it. So therefore, the specific heat capacity is 16,524 divided by 1 times 16. This gives us 1032.75 joules per kilogram degrees Celsius. Sources of error include low or no insulation. The final value for specific heat capacity will be too high because some energy is transferred to the surroundings and not to the block. Also, the block takes time at the start to heat up, so you might get an incorrect reading for temperature rise if you don't take that into account. So this is required practical 1 for GCSE physics. Next, we're going to take a look at power and energy transfers in systems. Power. This is the rate of energy transfer or the rate of work done. The rate just means how quickly this happens. Energy transferred is the same thing as work done. Those two things are the same. The two equations that we need to be able to use, which again will be given, are power is energy transferred divided by time, energy transferred in joules, time in seconds, and power is in watts. The second equation is power is work done divided by time, work is in joules, time again is in seconds, and power again is in watts. However, important to remember that watts is the same thing as joules per second. 10 watts means 10 joules per second. Here are two electric motors, motor A and motor B. Let's say both motors do the same work and transfer 40 joules of energy to raise the weight. Motor A takes 10 seconds, motor B takes 20 seconds. So the power for motor A is 40 divided by 10, which is 4 watts, which is 4 joules per second. And for motor B, it's 40 divided by 20, which is 2 watts, which is 2 joules per second. This means motor A has more power because it took less time to transfer the same amount of energy in joules. Next, we take a look at energy transfers in a system. Remember, energy cannot be created or destroyed. However, energy can be transferred usefully, it can be stored, or it can be dissipated or spread out to the surroundings. Examples include a mobile phone. We have energy input into the mobile phone. Some energy will be stored in the battery. Some will be transferred as sound. Some will be transferred as light. And some will be transferred as heat. Important to remember that sound and light are transferred usefully, and the heat is not so useful to us, and it's also dissipated and spread out into the surroundings. One more example, we have a washing machine. Energy is transferred as heat and as kinetic, and some as sound. We might say heat is transferred usefully if we're washing at a warmer temperature. Kinetic is going to be useful, and therefore the sound, this is dissipated or spread out into the surroundings. So that's 2 examples of energy transfers in a system, and the fact that it can be transferred usefully, stored, or dissipated. Also important to remember that energy is eventually dissipated in all systems. In a closed system with energy transfers, there's no overall change in the total energy. This is kind of an imaginary system because this doesn't really happen for real. However, if we were to say this is a closed system and we have a car, we have a chemical energy store either in the fuel or in the battery. The energy is transferred as kinetic, let's say 540 joules, sound as 160 joules, and heat as 300 joules. Sound and heat are dissipated and spread into the environment, and the kinetic is the useful energy transfer. The total energy output is equal to the total energy input. So let's say the input is 1000 joules. If we add up the kinetic, sound and heat, we'll see that that adds up to 1000 joules as well. The output is 1000 joules. Important to remember, all energy is eventually dissipated and stored in less useful ways, often described as wasted. In the above example, sound and heat are wasted and spread to the surroundings. So this is the idea of power and energy transfers in a system. Next, we take a look at reducing unwanted energy transfers. Moving parts often have friction between them, and friction transfers energy as heat to the surroundings. Using lubrication reduces friction and so reduces heat transfer to the surroundings. We have less wasted energy. Let's go back to our motor for an example. Moving parts in the motor cause friction and release heat. Heat is transferred to the surroundings. However, lubrication with oil reduces friction and reduces heat transfer to the surroundings. That means more of the input energy is transferred as kinetic rather than lost or wasted as heat. Another example, hot water tanks store hot water in houses. Here's a hot water tank. The problem is they transfer heat to the surroundings. The heat energy is wasted. We want to keep that energy in the water and not transfer it to the surroundings. So we can reduce the heat loss with thermal insulation. There's our thermal insulation on the tank and any hot water pipes leaving the tank. That means less heat energy is transferred to the surroundings. So, 2 methods for reducing unwanted energy transfers. The first one is lubrication, and that's used for moving parts, for example bike chains, car engines and motors. And how it works is it reduces friction between surfaces in contact so less heat is generated. For thermal insulation, it's used in buildings to keep buildings warm, hot water tank and even clothes to keep people warm. And how it works, there is less conduction, radiation and convection. We don't need to know huge details about convection, however, this is how thermal insulation works. Next, we're going to take a look at reducing heat loss in buildings. Heat energy is lost through walls and is affected by the thickness of the walls and the thermal conductivity of the walls. Let's take a look at that in a bit more detail. Here is a building, a house, and we have the idea that the thicker the walls, the slower the rate of cooling of the building. We also have the idea that if we have different materials with different thermal conductivity, that the higher the thermal conductivity of the material, the faster the rate of cooling of a building. The best combination for insulating a house or a building is to have thick walls made of a material with low thermal conductivity. Next, we take a look at thermal conductivity of metal rods. This is not a required practical. It's mentioned in the spec and has lots of really good skills that you could use in practical questions. So this is how it works. We have a metal rod. We have a pin attached with some wax to the metal rod, and we heat one side of the metal rod. Heat is conducted along the rod, and we measure the time taken for the pin to drop. And the pin drops because the heat melts the wax. The lower the time for the pin to drop, the higher the thermal conductivity of the rod. The independent variable in this experiment is the type of metal, for example, copper or iron, and the dependent variable is the time for the pin to drop. The control variables include the length of the rod, the thickness of the rod, the mass of the wax used, the weight of the pin, in other words, use the same type of pin. Results will be on a bar graph because the independent variable is categoric. A categoric variable is described by words, for example, copper, iron, and so on. Another thing to mention is that we would repeat each metal experiment 3 times and take a mean. The bar graph would look a bit like this, the type of metal on the x-axis along the bottom and the mean time for the pin to drop on the y-axis. Next, we take a look at required practical 2, and this is for triple science students only. This is to investigate the effectiveness of different materials as thermal insulators and the factors that may affect thermal insulation. 2 key experiments. One is the type of material used, and the second one is the thickness of the material. The first experiment is the effect of type of material. This is the method. We would line a large beaker with your insulating material and then put a small beaker inside the larger beaker. So here's a larger beaker. We've lined it with our insulating material and the smaller beaker goes inside. Large beaker there, insulating material and the smaller beaker. We would put 80 centimeters cubed of hot water into the small beaker. We would make the water hot using a kettle. And we would put a cardboard lid with a hole and a thermometer into the beaker or into the water. There's our cardboard lid and there's our thermometer. We would record the start temperature of the water every 2 minutes for 20 minutes. Remember to let the thermometer get to temperature before we start timing. We would repeat with each of 4 different materials, which gives us a total of 5. The independent variable here is the type of material. The dependent variable is the temperature. The control variables are the volume of water, the start temperature, the surface area of the beaker, and the thickness of the insulating material. Our graph might look a little something like this. We use line graphs because we're measuring temperature versus time in minutes for each different material. Cotton wool is at the top, bubble wrap, felt, tin foil, and no material. These are just examples of the types of material that you might use. Second experiment, the thickness of material by adding layers, for example, newspaper. We would put 80 centimeters cubed of hot water into a beaker. There's our 80 centimeters cubed of hot water. We would then put a cardboard lid with a hole and a thermometer into the beaker. We would then record the start temperature of the water, then every 2 minutes for the next 10 minutes. We would add 1 layer of insulating material and repeat steps 1 to 3. We do this for 0, 1, 2, 3 and 4 layers of insulating material. Our independent variable is number of layers. The dependent variable is the temperature. Our control variables are the volume of the water, the start temperature, the surface area of the beaker, and the type of insulating material. In this case, it's all newspaper. Here's our graph of our results, what they might look like. Again, we're plotting time against temperature for the different numbers of layers. So no layers first as a comparison, then 1 layer, 2 layer, 3 layers, and 4. So those are the 2 parts for required practical number 2. Sometimes they ask us to make sure the experiment we design is valid. So validity is to repeat the experiment, the type of material or the number of layers, and take a mean. And is in bold there because you must include the idea of taking a mean and not just say repeat the experiment. The control variables are the same volume of water, the start temperature, and same thickness of material for one of those experiments, but for validity we must mention the control variables. Sometimes they ask for a risk assessment. This includes hazard, risk, and prevention. So an example would be the hazard is glass, the risk is you could break the glass and it could cut you, and the prevention is to keep glass away from the edge of benches and handle with care. Another one is hot water, which could cause burns. We would handle with gloves or with tongs so that we don't touch hot objects. Also remember, having no insulation acts as a control experiment, and a control experiment is used to compare and see how effective the other materials are. So that's required practical 2. Next, we're going to take a look at efficiency. Efficiency. This is the percentage or proportion of input energy in a system that is transferred usefully. Here's a couple of motors. Motor 1. The total energy input is shown by this block. The useful energy is shown in green, the useful being kinetic energy, and the wasted is shown in red. For motor 2, we've got the same total input energy, but you can see a greater proportion is useful for motor 2 than is wasted. Wasted energy is transferred to the surroundings as heat and sound. So the equation that we need to be able to use and is given to us is efficiency is useful energy output transfer divided by the total input energy transfer, often said as a percentage, so we would times that by 100 to get the percentage. A second way is useful power output divided by total power input, again times 100 to get a percentage. So motor 1 input energy, let's look at some sample data. Let's say we have 960 joules of input energy, transferred to kinetic is 640, so the efficiency is 640 divided by 960, which is 0.67, times by 100 gives us 67%. For the second example, there's an extra step. The useful input energy is 960 and transferred to heat, in other words wasted, is 240. How would we calculate the efficiency? Well, the useful is 960 minus the wasted, which is 240, that's 720. Then we have 720 divided by 960, that's 75%. Motor 2 is more efficient as a bigger proportion of the input energy is transferred usefully as kinetic energy. Next, we look at national and global energy resources. Main energy resources available are the non-renewable ones, which are resources that have a finite or limited amount and cannot be replenished as they are used. These include the fossil fuels, which are coal, crude oil, and natural gas. And we also have nuclear fuel, which is not a fossil fuel, but it is also non-renewable. Renewable resources are ones that can be replenished as they are used. This includes wind, hydroelectric, tides, water waves, geothermal, sun, and biofuels. These energy resources are used for transport, electricity generation, and heating. Now, the main uses for the ones above, it's not the only use, but the main uses for coal are for generating electricity. There are other uses. We have transport for crude oil, but again, there are other uses. Natural gas is mainly heating. Nuclear is mostly electricity generation. For wind, hydroelectric, tides, and water waves, this is mostly electricity generation. Geothermal is also electricity generation. The sun can be for electricity generation or for heating, if we have solar panels for heating water. and biofuels are often for transport. Remember, these are the main uses, but there might be more than one use for each of these energy sources. Fossil fuels are reliable, however, burning them releases carbon dioxide, which contributes to the greenhouse effect, and sulfur dioxide from coal and oil, which can produce acid rain. Fossil fuels are also running out because they are non-renewable. Finally, reliability and use of energy resources. Hydroelectric. This is where water falls from a high point to a low point and turns turbines. This is reliable as long as water is available. We have the sun as an energy source. This is unreliable because it depends on the amount of sunlight, the time of day, the weather, cloud cover, and the season. Wind, again, this is unreliable because it depends on the wind blowing. And we have geothermal. This is hot water pumped down to hot rocks, which is heated, turned to steam, which turns turbines for generating electricity, and the reliability of this is high. For tides, this uses the tide movement, water coming in and out to generate electricity. This reliability is high because you will always have tides. Waves uses the movement of waves to generate electricity. Again, this is unreliable because it depends on the wind producing the waves and it depends on the presence of waves. We have biofuels. These are reliable as long as crops are available to produce those biofuels. So this is efficiency and national and global energy resources. Remember, you can become a member of the channel and access all Paper 2 whole unit videos and some of the physics videos as well. Thanks for watching, and I'll see you soon.